In this lecture, we are going to really dive into quantum field theory. Specifically, we're going to spend a lot of the beginning part of this course on just something called the scalar field theory, which will make more sense as time goes on. As we get further into the course, we'll start getting into things like spinors and spin one fields and into a field called quantum electrodynamics. But it really is instructive to just focus on what we call scalar theory, which is really what we're going to start with. And this really gets us to the heart of what quantum field theory is about. This is probably the most important statement of the whole course. It says that quantum field theory is nothing but a direct extension of ordinary quantum mechanics of multiple systems. So I gave a lecture, the first lecture of our series was on regular quantum mechanics. It's worth reviewing that. I'm going to actually review a lot of those topics here again. But really, quantum field theory is nothing but the extension of quantum mechanics to multiple systems. There's not really very essentially new principles. The math gets a little bit harder, but it's important to remember this statement. Quantum mechanics, I've spent a lot of time self-studying it. It often gets presented in sometimes a haphazard way, depending on which books you look at. There's some outstanding books. But there's a certain order in which ordinary quantum mechanics ought to be presented, and the same applies to quantum field theory. In ordinary quantum mechanics, after we describe what we mean by our physical system in real life, in the real world, we have to quote unquote quantize it. But that really means doing the following things. The first thing is you have to define precisely what is the Hilbert space. Remember, the Hilbert space is the main mathematical area in which quantum mechanics operates. It says that every physical system is some ket in some Hilbert space. So you have to define very clearly mathematically what is the Hilbert space of the system you're talking about. Second, there are certain operators that come into place, and operators act on kets in Hilbert spaces, and you need to define precisely what the action is of certain operators on kets in this Hilbert space. After you've done that, the most important operator is called a Hamiltonian. You need to postulate the form of that depending on what physical system you're talking about. In this talk, we're really just going to focus on the first two parts. In the next couple of talks, we're going to get down to part 3. But it's important to first define what you mean, what the Hilbert space is and what our operators are. That really takes us far. And I think part of the confusion that happens when I've learned quantum field theory from different textbooks is these first two parts are not always explicitly laid out. And that's what I hope to do now. Here's the big basic idea. If we think of all of space and we coordinatize it with an x, y, and z axis like this, for example, we just break up all of space into lots of really small cubes. Each of these cubes are called voxels or voxel elements, or that's what I call them at least. It's very similar to a pixel or a picture element on a two-dimensional screen, like on your iPad or on a television screen. But the idea is that each of these are little cubes, and they totally fill the space. We'll talk about going back and forth between the continuous and discrete representations, but I think for a large number of things, I think it's important to think of it as these cubes are discrete, meaning that they're really, really small, but they're not zero. They have a very, very small edge length to each of them. If you think of it that way, it allows you to be discrete and be a little bit more clear in your thinking. In each of these cubes, or voxels as I'll call them, we assume there's a scalar. If you remember back on the previous course, on the previous lecture on quantum mechanics, I talked about a ball going up and down a one-dimensional track. That's exactly the same picture that I'm going to use here. In each voxel, we assume there's a scalar. This really means that there's a point that can move up and down in one dimension. So we call it a ball on a track, but really it's a point because it has no three-dimensional structure, and there's only one or two things it can do. It can move up or it can move down. This track can be either discrete or continuous. Again, we go back and forth with these ideas. I'll just mention, as I mentioned before, that sometimes I'm going to use a discrete representation for things, and sometimes I'll use a continuous representation for things. It's tempting to just say I'm going to do one representation and be consistent throughout the course, but there are certain arguments that are much easier explained with the discrete representation and vice versa. So most of the time I'll be using discrete, but sometimes I'll go back and forth. And it's also good because different books work in different ways. So for this particular representation, this ball can either just move up or down. And this ball exists in this voxel. And in this picture, I have little rungs of this ladder. It tells the ball can jump here, 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 or here, here, here. This, if we assume that the ball is only on the rungs of the ladder, would be a discrete representation. At a different point in space, I have a different voxel, but the same exact structure. There's another ball at that point in space and another one-dimensional track, and the ball can just do exactly the same thing, move up or down. So we have two balls and two tracks in this particular case. And the idea in quantum field theory is that I break space up into a million voxels, and each voxel has one ball on one dimension, on one-dimensional track. We have to have a way of labeling or naming these voxels. And the best way of doing it, instead of saying A, B, C, D, E, F, G, you're just going to run out of voxels very fast because there's a humongous number of voxels here. We just name each voxel by the position at which it's located. For example, you can say the position of the center of the voxel. This voxel, for example, might be at the point x1, y1, z1, and we just call it voxel x1, y1, z1. Now we follow standard quantum mechanical procedures. Mentioned before, hopefully the assumption of this course is that you've taken a quantum mechanics course. I have a brief review on the previous lecture about quantum mechanics, but we're going to review a lot of those concepts here. But now we just do our standard quantum mechanics stuff. We defined our physical system. Let's just, for example, talk about one voxel for now. This is voxel x1, y1, z1. And there's a ball that can move up or it can move down in these, let's say, discrete amounts. Consider the observable. In this case, we call it phi, and phi will represent the height of this ball, whether it's up or down. That's the observable that we're measuring. This part's kind of dramatic, but actually important. We have to think of, even though no one has quote unquote ever seen it, at every point in space, there really is a voxel and there really is a ball that's moving up or down. And this ball can really only just take certain amounts in this discrete representation. Think of it like that. That's our physical system. You may say, well, I've never seen anything like that at every given point in space in real life. We almost have to imagine that there really is, if we had a strong enough microscope, that there really is at each point in space a voxel and a ball moving up and down on a one-dimensional track. And we could, in principle, measure, if we had a really good measuring apparatus, exactly where that ball is on this track. So that's our physical setup. Now, in quantum mechanics, we have to quantize our system, which goes through certain prescription. We associate to this physical observable phi an operator. In this case, I call it phi hat. I give it the name x1, y1, z1, just to imply that it's associated with this voxel. That's all that really means. The set of all possible values we can obtain when we measure phi will correspond to kets, and you can call those kets Q1, Q2, etc., with a subscript to tell you which voxel it came from, x1, y1, z1. And these are the eigenstates of this operator, of the phi hat operator. So it's just like in standard quantum mechanics, we used to call this thing x. Here we're calling it phi, which represents the position of the ball in this one-dimensional track. And the eigenstates of that are Q1, Q2, etc., all the possible values that this can take. The set of all linear combinations of these eigenstates, Q1, Q2, etc., forms the complete Hilbert space at the voxel, just like in standard quantum mechanics. That's our Hilbert space, and this is the operator that we've so far defined, the position operator of the ball, which we call phi. At any given time, in classical mechanics, this ball is either is only in one particular spot at any given point in time. We know from quantum mechanics that everything exists in a potential superposition of states. So at any given time, the state of our system, according to quantum mechanics, right now our system is just one ball on a 1D track, that's all we're talking about, is given by a ket in the Hilbert space. That ket is usually symbolized by something like this, psi. is equal to some linear combination of the basis vectors, q1, q2, q3, with the alpha 1, alpha 2, alpha 3 being the weights of the various kets, or the weights in the superposition. At any given time, that's our system. According to quantum mechanics, if that's the state of our system, if we do an experiment and measure the position of the ball in this voxel, we can, in principle, get any value. Not just, it's not, we'll find that it can be in any particular value. And the probability of us measuring, for example, Q2, when we do the actual measurement, we'll see only one value. But the system is actually existing in a superposition of states. The probability of us measuring, say, this value, Q2, is, according to quantum mechanics, obtained as follows. You take the coefficient, alpha 2, which in general can be a complex number. So you take its modulus, and then you square it. What's the probability of us doing a measurement and finding out that, oh, the ball really came out as a measurement in Q3? Well, same thing. You take the coefficient, modulus of that, and you square it, etc. Standard quantum mechanics of the position of a ball on a one-dimensional track. What is the effect of the phi hat operator? Well, if we want to know the effect of the phi hat operator, we can talk about its effect on a typical basis vector. In this case, we use the basis vector, which we talked about before, q sub n, which is the eigenstates of q, which are the eigenstates of the phi hat operator. So that just acts in this standard way as follows. The phi hat operator acting on q sub n just gives us back q sub n multiplied by its eigenvalue q sub n. For example, if q sub n is the position 23.74, the ball's up higher on the track at the level of 23.74, the phi hat operator on that gives you the same exact ket or vector pre-multiplied by the coefficient 23.74, the eigenvalue. The effect of this operator, the phi hat operator on a general ket, is determined just by this rule and linearity, which is assumed of our real operators. Our real operators are supposed to be Hermitian and linear. And linearity basically means this, that if this is our generalized state as a superposition of basis vectors, this phi hat operator acting on psi, this generalized state, is just this applied to each one of these terms. So it hits this, and it pulls out the Q1, and it hits this, pulls out the Q2, it hits this, pulls out the Q3, so on and so forth. Pretty standard review of quantum mechanics for people familiar with it. Our other big operator is what we call the momentum operator, or in this case, the local momentum operator. And this is usually symbolized in quantum field theory as pi, or pi hat for now. This is the equivalent of p in standard quantum mechanics, just like phi was the equivalent of x in standard quantum mechanics. The easiest way to understand the pi or pi hat operator is its effect on the ket psi when psi is expressed in the continuous q basis. So here for a moment, I'm going to go back to pretending the ball on the 1D track can actually assume continuous rather than discrete values. In other words, it can go between rungs of the ladder if it wants to. The standard way of expressing this in quantum mechanics is that if we have a generalized state psi, that's still equal to a sum of all the different basis vectors. But because the basis vectors take on continuous values, we change the sum to an integral over dx. And then the coefficient is called a wave function psi x. And that tells you the weight of each particular position x. So this is one way of writing that. It looks more complicated, but it's really just a sum over a continuous value, which becomes an integral. And that's what the wave function in this Dirac or ket notation is, really just the coefficient of these terms. If you express it in this way, it's easy to understand the effect of the localized momentum operator. In this case, we're just calling it pi hat. This is just the same as in quantum mechanics. That pi hat acting on a general vector in our Hilbert space is just given by this expression. We basically just take the derivative of psi, the wave function, multiplied by minus I, and then that changes this wave function, and then we apply that to this entire integral summation. I will have you recall, as I mentioned in the previous lecture, in quantum field theory, we always use units where h bar is equal to 1 and the speed of light is equal to 1, and we can justify this by in physical terms, and then apply by changing units, and we can apply h bar and c at the end if we want. So you may recognize this formula as minus I h bar d dx, but h bar is going to be equal to 1. We're going to set our units in such a way that makes everything a lot simpler for later on. Is it possible to understand the momentum operator in a discrete representation? The answer is yes, and I think this is mentioned a lot in quantum mechanics, but this is the basic idea you can do. You can take this ket psi and express it now in a discrete fashion as this actual sum, not integral. What is the effect of the pi hat operator in this representation, in the discrete representation? Well, it's the same idea as the integral. You first say that, all right, this pi hat operator is supposed to change this vector in our Hilbert space. So every vector can be expressed as a linear combination of basis vectors. Let's just say we stick with our basis vectors q1, q2, and q3. Now this pi hat operator just changes the coefficients of each of these to give us a new vector. And how does it change the coefficient? Well, if you look at the q1 basis vector, you see what the original representation was before pi hat operated on it. And you look at q1, its alpha value, and you look at q2 and its alpha 2 value. And you just take the difference between the two, alpha 2 minus alpha 1, divided by a, and a is just considered some standard separation. It's really the distance between rungs of the ladder. If we're talking about a discrete representation, a is not infinitely small. It has a very small but still finite value. And you do a similar thing with Q2, where you basically look at Q2 and you look at the next step up, which is Q3, and you look at the coefficient of Q3 minus the coefficient of Q2 divided by that same constant A. And this really is the effect of taking the derivative. We look at one step and the immediate next step up and look at the coefficients between the two, subtract the two, and divide it by the standard distance between rungs of the ladder. This is the momentum operator in the discrete representation, which here we call pi or pi hat. That summarizes what happens in one voxel. We've now quantized one voxel. Remember, we're really thinking at every single point in space, there really is this tiny ball that's moving up and down on a 1D track. You can't see it, but we pretend it's really there, and that's what we've just quantized. Now, we just mentioned that space is not just one point, it's multiple points, and at each point there's a voxel. Before getting into an infinite number or a humongous number of voxels, let's just think of a two voxel system. Pretend that space has two voxels, one over here and one over here. We'll call the first one voxel A and the second one voxel B, and we can label that in different ways. We can say x sub 1 with this 3D vector notation is x1, y1, z1. I might even talk in a little bit about changing y and z to x2, x3. We'll get to that in a little bit, but let's just call this voxel A and voxel B. Associated with voxel A, we have a local Hilbert space, as we talked about on the previous slides. The basis vectors for this voxel are just like we talked about, q sub 1, q sub 2, q sub 3 in this discrete representation. Notice that we just have a subscript here, which tells us that this came from voxel A, which is also called x1, y1, z1 in this picture. Similarly, associated with voxel B, we have another local Hilbert space. The basis vectors for that local Hilbert space are similarly expressed as these are identical in structure, as we mentioned earlier, q sub 1, but now the q1, and then the subscript here is x2, y2, z2, just telling you this came from voxel B, and so on and so forth. And as we mentioned, voxel A and B have identical physical structure. At each point in space, there's this identical one ball on a 1D track moving up and down. Here's the big point. In quantum mechanics, when you have two subsystems, a subsystem A and a subsystem B, and they're combined to form a larger system, what rule does it follow? Well, according to the laws or principles of quantum mechanics, you have to use the tensor product of the two Hilbert spaces, and that's the new Hilbert space that the physical system will be represented by. I think one of the best descriptions of this I've seen are in Barton's Weebox book. He's an MIT professor that has a wonderful online course and the textbook on quantum mechanics, and he really explains the tensor product well, and even talks on his online course about how it's sometimes misrepresented in standard textbooks of quantum mechanics. But it really should be a principle of quantum mechanics. So according to quantum mechanics, the combined two voxel system will be represented mathematically by a new, quote, larger Hilbert space. So I'm just going to use the word larger Hilbert space. We had a Hilbert space here, Hilbert space there. When we combine the two, there's some, quote unquote, larger Hilbert space. This larger Hilbert space is formed by taking the tensor product of the basis vectors of the local Hilbert space of the individual voxels. Meaning this, I look at this voxel, which is voxel A, and I grab a basis vector from it. For example, I can grab the first basis vector called Q1. I cross it, which is just a symbol called the tensor product, with a basis vector from this voxel, which is voxel B, or x2, y2, z2. I do the same in every possible thing. I grab a basis vector from here, and I cross it with another basis vector from here. So for example, here I can also still grab the first basis vector from A, cross it with the second basis vector from B, and I just imagine doing that for every possible combination of basis vectors taken from A and B. And then when I write the symbol across, I think of this whole thing as just one huge quantity or one huge mathematical object, which itself is a vector in a larger Hilbert space. I'll get to this in a moment, but just wanted to show you one thing. Apologize. This is going to be a vector in a larger Hilbert space. This is a vector in a larger Hilbert space. And what I can end up doing is I can, just because these are vectors in a Hilbert space, I can multiply this by some coefficient, like a complex number. And I can multiply this by a complex number, and I can add vectors. Like this whole thing can be added to this whole thing, and I could take some linear combination of these things. And that gives me my new um, vectors in the larger Hilbert space. The tensor product has some mathematical definitions, which can be described as follows. I'm not going to harp on this too much, but it's worth going over it a little bit just to get us a little bit more familiar with it. So whenever I form a tensor product, I take some vector from my Hilbert space A, and I cross it with some vector from my Hilbert space B. Let's say I take the vector from my Hilbert space A, but before I cross it, I multiply it by some complex number to form a new ket in Hilbert space A, and then I cross that with a ket in Hilbert space B. Well, according to the rules, the mathematical rules of the tensor product, which quantum mechanics assumes is a physical law, represent our combined subsystems. Then, according to those rules, this is what I get. I can take this constant C1 and pull it out, and just take the standard tensor product of A cross B, and multiply that by this same coefficient C1. So just to follow the math, this is a ket in Hilbert space A, this is a ket in Hilbert space B. I'm crossing them, then I get a ket in this larger Hilbert space, and then I can pre-multiply that by that same constant C1. And the same thing applies to the second position. The other rule for tensor product is a summation rule, where that if I take a vector in Hilbert space A, but that vector itself is a sum of vectors in Hilbert space A, A1 plus A2. And if I cross that with B, I get this formula here, where I have this thing, A1 crossed with just B, and then this thing, A2 crossed with just B, and then this whole thing is a ket in the larger Hilbert space. This is a ket in the larger Hilbert space. Sorry, I forgot to do that. And then I can add the two, because now this is a ket in Hilbert space, this is a ket in a Hilbert space. In every Hilbert space, you can add vectors or pre-multiply them by a constant. This is what I started saying before. The newly formed tensor product kets are themselves, by definition, the basis vectors of the larger Hilbert space. Any new ket in a larger Hilbert space, therefore, is a linear combination of these basis vectors. For example, after I've combined my subsystem A and subsystem B, which each have their own Hilbert spaces, I form this larger Hilbert space. And here's a ket psi in our larger Hilbert space. And that's just the linear combination of the basis vectors. And the basis vectors, as I mentioned, are some basis vector from A crossed with some basis vector from B. This whole thing is one object. This is a basis vector from A and the second basis vector from B. The whole thing is one object, so on and so forth. And each of these whole objects are pre-multiplied by some constant, beta 1, beta 2, for example, beta 325. And this is what it means to take a linear combination. And just like before, these beta 1s, beta 2s are just numbers. For example, complex numbers are real numbers. If you want to get back for a moment to thinking about the continuous representation, which is sometimes worth thinking about, let's say the balls on the track are not just confined to the rungs of the ladder, but can be any real number going up or down, in other words, between the rungs of the ladder. Then we can still define things as follows, that we think of a ket in this larger Hilbert space as a wave function of two now continuous variables, where I take the position of the ball in A, which is now a continuous variable, which I still call QA, and the position of the ball in QB. And then I can sum those in an integral sum, which I'll show you in a second. And this and the coefficient of that is still called psi, or the wave function. So technically, if you want to follow it, it looks something like this. It looks complicated, but it's really not. It just says that we're taking QA cross QB, which means we take every possible value of QA and every possible value of QB. But because it's continuous, we have to use an integral over dq, integral over dqb, and integral over dqa. And then the coefficient of each of these sums is called the wave function psi. And you plug in qa, plug in qb, and you tell it what the coefficient is. So this thing acts like a wave function, which is really a multivariable function of two variables, one qa and qb. You give me a qa, you give me a qb, and then I output a number, which is some complex number, which represents the coefficient. Is another way of looking at things, and I'm sorry to keep harping on this, but these ideas become important, and it's important to be clear on what they are. I can write down all my basis vectors, something like this. Here's voxel A, here's voxel B, and that's true for all of these. Here I have the first Q1, which came from voxel A, crossed with Q1 from voxel B. If I go this way, I think of another basis vector where I keep it at Q1 crossed with QB, the second basis vector from QB, keep Q1 at the same, and then the third basis vector at QB, so on and so forth, going this way. But if I go up this way, I write my basis vectors as Q1 cross Q1, and then the next one I change QA to the second basis vector cross Q1 going this way. This is kind of one way of writing down all your possible basis vectors. And this shows it in the discrete form, but you can kind of imagine the same kind of picture in a continuous form. As I go up here, I change psi A. As I go this way, I change psi B. And these are all just basis vectors. Remember, a single ket, if we have our system of A and B, and we're talking about its physical state at any given point in time, that's a linear combination of all these basis vectors. So to actually specify it, I have to have a weight to each of these basis vectors, psi 1, 1, psi 2, 1, psi 3, 1, psi 4, 1, so on and so forth. And one of these particular linear combinations is the physical state. It's just one ket that represents the state of our system right now. We need to also be clear about our operators. Remember when we talked about our one voxel system, we had an operator called phi or phi hat, and we had another operator called pi or pi hat, one corresponding to the position of the ball and the other one corresponding to the momentum of the ball. Well, now we have a larger Hilbert space because we've combined two voxels. So what kind of operators do we have? Well, it turns out we can still inherit operators from the original Hilbert spaces and quote unquote promote them so that they have a well-defined mathematical function on our larger Hilbert space. Let's, for example, assume that we have some operator called omega hat that originally came from Hilbert space A. We can, in a very natural way, define omega hat which originally came from A, but now applied to the larger Hilbert space, which is called A cross B. A cross B is the name of the larger Hilbert space. And we can define the action of that on the larger Hilbert space as follows. The action of this on the larger Hilbert space can be defined by its action on a typical, for example, vector or basis vector. And all it is as follows. Here's a ket in the larger Hilbert space. And how does this new promoted operator act on it? Well, you take the omega hat and you just apply it to this A1. This is well defined. Remember, this thing originated from just the A Hilbert space. So this operator just hits A1, and that's well defined. You take that result and you cross it or do a tensor product with just nothing but the original B1. So associated with this is an implicit identity operator that just hits the second part with the identity, which means it keeps it the same. And the first part is hit in the standard way. So now this whole object is a new object. It is a object in the larger Hilbert space. So it takes an object from the original. It takes an original object in a larger Hilbert space and converts it to another object in a larger Hilbert space. So in this way, it took our operator, which is only defined on the A subsystem, and now it allows it to operate on the larger Hilbert space A cross B. It's a standard way in which we promote operators. We could do the same thing with operators from the B subsystem. Some basic examples just to make sure everybody's clear. Let's just say we have voxel A and voxel B, and we have this operator, which is our position operator or phi operator that came from voxel A. But we want to promote that to an operator that's now going to operate on our larger Hilbert space of A cross B. And really, one way of writing that is this, I didn't mention this in the previous slide, but you take this operator, cross it with an operator here, and this part of the operator is only going to operate on the A part, and this part is only going to operate on the B part. What does that mean? Well, again, as we kind of showed on the previous slide, if we take this promoted phi operator, which came from the voxel A, and just define it on the A cross B, if it operates on, for example, this standard basis vector of our larger Hilbert space, you'll get the following. It's going to hit this part, just pull out the Q13, and keep this eigenstate the same. On the second part, it literally does nothing to change this at all. By our rules of tensor product that I mentioned, we can pull out this constant as follows, and we get this over here, which this again is an element in our larger Hilbert space, just pre-multiplied by Q13. So in kind of a very standard way, but now mathematically well defined, we can promote operators to operate on this tensor product of Hilbert spaces. How does the momentum operator get promoted? Well, in a similar way, but it's worth it to kind of think about things at least once in a while. Again, this is sometimes I find a helpful way that I've thought about to write our basis vectors, going this way and going this way, and just list them all. And for a given ket, there's a weight to each one of these basis vectors as depicted here. The pi a operator really acts as follows. Now this is kind of getting back to the discrete representation. Well, I have to, in order to define the action of the pi a operator on the combined Hilbert space, I should actually have a superscript here on A cross B. Well, I just have to define how its action is on any one of these basis vectors, how it changes the coefficient of them. So for example, how does it change the coefficient of this, psi 2 cross psi 2? Well, the way I do that is if I'm talking about the pi a operator, I look at this coefficient for this basis vector, and I look at the next adjacent basis vector when I go up in the A direction. I only change the A voxel, which is up here, and I look at that coefficient. I just take this coefficient, psi 3, 2, minus this coefficient, psi 2, 2, and I divide it by the standard spacing between rungs of the ladder A. And that's the new coefficient for this basis vector. This gets changed to this. And that's how the pi a operator acts. And I could do the same for any one of these. And I should do the same for every one of these to get a whole new ket or a whole new linear combination of basis vectors. So that is the function of this. This is really the same type of thing as a partial derivative. I take the partial derivative of this quote-unquote wave function when I only change up in this direction and keep this direction constant. The pi b operator, which came from the B voxel, is the same thing, except I go in this direction. So if I want to, again, see how this basis vector's coefficients get changed. I look at this basis vector and I look at the next biggest one, but going this way, and I look at the coefficient of this guy, psi 2 cross psi sub 3, which is this, subtracted from the original coefficient of this, divided by the same spacing of the rungs of the ladder A, and that is the new coefficient of this basis vector. And I do that for every one, and this tells me in a very mathematically clean way how the pi b operator acts on the combined Hilbert space. And this is really just like the partial derivative, so to speak, if you change this way and don't change this way. So far, we have two voxels that were combined to form a larger Hilbert space, and we promoted operators like phi hat from A and phi hat from B, and pi hat from A and pi hat from B. But are there other operators? Well, yes, there are. We can come up with operators that now take advantage of the fact that we have two voxels and aren't specifically derived only from one voxel. The classic one is this, which will come up in quantum field theory over and over again, and you can call it whatever you want, but it's the partial derivative of phi with respect to a spatial coordinate xi. And this xi can represent x, y, or z axis, and eventually we'll start talking about that as x1, x2, and x3. But this is how you phrase it, and here's how it's defined. Suppose our two voxels are side by side on the x-axis with the spacing dx. This operator, d phi dx, operates on the large Hilbert space as follows, kind of exactly the way you would think. D phi dx is equal to the phi b operator minus the phi a operator divided by dx. Now, just to be mathematically clear again, this whole beast here, this whole construct, is supposed to operate on the larger Hilbert space, A cross B. And what that means is that this phi b is really the promoted phi b operator, which we've talked about as I cross phi b. And this phi a operator is the promoted A operator, is phi a cross I. And to say you're dividing something by dx really just means you're multiplying it by 1 over dx. And then when you have a sum or a difference of operators, you can apply each of these to the individual cats, just like we do in quantum mechanics. So just to be explicit, this operator d phi dx is equal to this. Let's say you want to see how it operates. As I mentioned, this is going to operate on a larger Hilbert space. So here's a typical larger Hilbert space vector expressed as the tensor product of something taken from the base from A, which is the 14th basis vector here, and the something taken from B, which is the 6th basis vector of B. How is this going to operate on this to change it? Well, it's an operator. It better be mathematically well defined. Well, I'll just write its definition as this. These are now promoted operators. What does this mean? Well, I can break it up into 1 over dx psi b, minus 1 over dx psi a, and then operates on this. This is standard for how operators work on kets from quantum mechanics. Now, what's the effect of phi b on this? Well, it's, as you know, it's going to be the identity on this, and it's going to hit this one. And for this particular case, phi b on this is going to, since this is an eigen state of phi b, you'll just pull out a Q6. Here, I apologize, the word is psi 6, but it should really be a Q6. And same thing with this here. And so this is the expression I'll get. Otherwise, it keeps this part the same. And same thing over here. For the psi a operator, it's going to pull out the Q14 and keep the rest of it the same. And what I can do is that since this part and this part are really the same thing, I can factor that out and just pull out the coefficient, and I get something very simple like this. Just for the typos here, Q6 minus Q14 over dx, and then this is the original larger Hilbert space ket, and this is its new coefficient. So that's the effect of this guy. It's very well defined mathematically. That's really the big point. We're going to start getting to things where we just talk about expressions of operators, and we have to be very clear that we know what the operator is, what the Hilbert space is, to make sure that things are clear and consistent. All right, so now we've talked about one voxel and all of its structure, its Hilbert space, and its operators. Then we talked about if we had two voxels that are combined to form a larger system and its operators and its Hilbert space. Now, in quantum field theory, all we need to do is jump up to a huge number of voxels, 3 voxels, 4 voxels, 5 voxels, until we eventually fill out all of our space. How big is our space? Well, these are other deeper questions, and somewhat philosophical questions and somewhat experimental questions. I'm just going to assume our space has n voxels in the x direction, n voxels in the y direction, n voxels in the z direction. So in total, we have n to the third voxels. As we mentioned, each voxel, I, for the most part, want you to think of as really, really, really small, but not infinitely small. So in other words, there is some sort of finite, but really small dimension to how big each edge of this cube is. And then we'll go back and forth. I will admit that, depending on what makes the derivations easier. And then within each cube, we think of, for the most part, usually discrete jumps of the ladder, but sometimes we'll go back and forth there as well. So the idea is that we go from 1 voxel to 2 voxel all the way up to n to the third voxels. And we follow exactly the same ideas as before. Each voxel has the same one ball in a 1D structure because space is homogeneous. We assume that there's nothing different about this point in space and this point in space. And there's voxels now, not just in 2 areas, but really nearly infinite or n to the third areas. Each voxel, again, has a name, and instead of calling it A, B, C, D, E, F, G, which would run out of letters really, really, really fast, we just give it the name of its coordinate. So when we say x1, x, y, z, or now we're going to get to the x1, x2, x3, which is common in quantum field theory with these superscripts coordinate, what we're really talking about is the voxel at this coordinate. So that's what its name is. At each voxel, there exists a local Hilbert space formed in exactly the same way as described above. Also, each voxel has the local operators, phi hat and pi hat. So every single one of these starts with their own local operators for the position of the ball and the momentum of that particular ball. This part's now important. In conventional quantum field theory, it's just a notational statement. It's conventional to drop the hat and just call these operators just phi and pi. So we're going to end up using operators like crazy, and it just gets exhausting to constantly put the hat in. So virtually every quantum field theory book that I've read, they eventually start getting rid of the hats. Once in a while, we'll use them because we'll get to parts of quantum field theory where these things actually don't represent operators; they represent numbers. But for the most part, just be used to this. We're going to start getting rid of the hats, but this thing here is really supposed to represent an operator. This thing is really an operator. In just a way we formed a large Hilbert space by taking the tensor product of 2 voxels, we now form a quote-unquote huge Hilbert space, that's what I call it, by taking the tensor product of all the local Hilbert spaces of each voxel. So instead of taking the tensor product of 2 things, we just take the tensor product of n to the third things. What does that mean? Well, a typical basis vector might look something like this. I go to my first voxel, and I looked at one of the positions of the ball, let's say position plus 0.1. I just have this subscript to tell me I got it from that first voxel. Then I go to the very next voxel, which let's just say is in 0, at the spatial coordinate 0, comma 0.1, comma 0, and I find some basis vector there. Let's say the ball at that point is 0.5. And I do the same thing n to the third times. And if I just do, and I put a cross product between all of them, and that entire thing is just one single basis vector in this huge Hilbert space, which is the cross product of all of this individual Hilbert spaces. To find another basis vector, I have to change each of these positions and take the cross product of all of them. And the same thing again and again and again and again. So you can imagine there's a number of basis vectors here, even in a discrete finite representation, are going to be enormous because you've entered the third voxels, how many different positions do you have in a discrete representation? How high can the ball go? How low can the ball go? But it's just a huge thing. But it's still, even though a large number of things, very well defined mathematically, unambiguously. A typical ket in this huge Hilbert space will be a linear combination of each one of these basis vectors. Same exact thing as other parts of quantum mechanics. If we want, if you want to go back to like a continuous type representation, you could think of things as a humongous wave function, which is really nothing but a multivariable calculus, but you have n to the third variables, which is an enormous number, not just 1 or 2 or 3. So you have the first voxel, you talk about the position of the ball in the first voxel, second voxel, the position of the ball in that one, so on and so forth, n to the third times. And for that particular basis vector, which is formed by the cross product, you have a weight to that basis vector. and that's called big letter psi, which is really like a wave function. And you do the same thing for each one of these things. And if you add all those things together with this weight, then you get a single ket in the huge Hilbert space. Says the same thing for each slot. For example, the first slot, we put in a certain position of the 1D ball in that voxel. The output is a complex number psi. The probability of this squared is this number squared is the complex modulus of this squared is the probability of finding the system in exactly that configuration. I also defined something else which makes life a little bit easier called a configuration. Let's just to be explicit, since we're talking about a large number of voxels, just trim things down a lot for a second. Let's just pretend that space is just two-dimensional for a second, and that we only have a total of 12 voxels that makes up all of our two-dimensional space. At each voxel, there's a ball that could be either up or down in a certain amount, and that's kind of depicted here. Here the ball is up, here the ball is down. The ball is this little green thing on my poor artistry, which I apologize for. The ball is going down over here. And this whole thing, I would just call this one configuration. This is one possible set of configurations of all the balls that you can have. It's really the specification of a single phi value at each voxel. Configuration 2 might be something like this. Is just some different configuration. The first two voxels, the ball is just sitting at 0. The other ones, it's down at some negative value, then at some positive value, so on and so forth. Think of that as the word configuration. It's just a specification of the position of the balls at every single point in space, at every single voxel. Now consider the set of all possible configurations. So for this 12 voxel object, think of this as every possible configuration you could have. Assign an amplitude, which is nothing but a complex number, to each configuration. Then sum all of these terms, and that whole thing represents a single ket psi of our huge Hilbert space. And that physically is the state of the system at that moment. Remember, from quantum mechanics, from classical mechanics, there actually is a position of the ball in an exact way at one given time. In quantum mechanics, things are a superposition. So here's one configuration, but here's another configuration, and the actual, at given time t, the actual system is in some superposition of states, and they're weighted by this complex coefficients psi. So this kind of shows it here as well. This huge psi for our small 2D system of only 12 voxels is something that is going to be something like this, where you have configuration 1 weighted by alpha 1 plus configuration 2 weighted by alpha 2, so on and so forth for all configurations, which even in just this 12 voxel example would go on forever. And that's the actual state of our system at any given time t. So this is what I call visualizing the quantum field. This to my knowledge, not really expressed in any textbook, but it's important to kind of understand this idea. That's what our quantum field theory really is all about. In the same way that we promoted operators when we had a 2-voxel system, we do exactly the same thing in an n to the 3rd voxel system. So this phi, which now again, notice I'm getting rid of the hat, operator that may be taken from this voxel, x1, x2, x3, gets promoted so that it can act on the huge Hilbert space, which is a tensor product of all of these voxel Hilbert spaces. And then each one of these, this psi operator, which came from here, can act on the whole Hilbert space. Another psi operator, which comes from another different voxel, can operate on the whole Hilbert space. Same exact thing with the pi operator. Operating the one I take from here, it can now be mathematically defined to operate on the whole Hilbert space. Our operators are very clearly defined now. Same idea between these partial derivative operators. So for example, this operator, the partial derivative of phi with respect to x1, I first have to define where I'm taking this thing from. So that, in other words, this thing is applied in this case to here, but this same operator is a different operator if I got it from this voxel versus if I got it from this voxel, if I got it from this voxel. So in other words, if I take the partial derivative, I get a different thing if I grab it from this location in space versus this location of space, which applies here to voxels. So just, to be explicit again, the d phi dx operator, which this particular one, which is coming from over here, is defined by 1 over dx, which might be the distance over here. And then the operator that's located at this point, it's promoted to operate in the whole Hilbert space, minus the operator that's taken from this point, that's also promoted to operate in the whole Hilbert space, but it's very clearly defined. That's the point. These expressions, which will come up over and over again in quantum field theory, as you'll see in our next lectures, have a very strict and clear mathematical definition. All right, so there's a long lecture, but an important one, and I'm going to just summarize it one more time. In quantum field theory, we imagine space is broken up into a huge number of voxels. Each voxel is a subsystem that contains a ball on a 1D track. We quantize each voxel in the standard way. This gives us a full quantum subsystem at that voxel. We have a local Hilbert space at that voxel, in this case x1, x2, x3, and we have well-defined operators at that voxel. The position operator, which we call phi, and usually called phi hat, but we'll get rid of the hat, and the pi or momentum operator, which will eventually get rid of the pi hat. We then form a huge Hilbert space by taking the tensor product of every single voxel, and we're assuming that there's something like n to the third voxels. There's a standard way of promoting operators such as this one and this one, the position and momentum operators taken from one given voxel, which originally come from a single voxel. We can also define other operators which aren't just defined from a single voxel, but things such as this partial derivative, d phi dx, for example, or d phi dx1. It could also be x2 or x3, which is y and z, respectively, taken at every point in space in a natural way. A configuration is a specification of an exact ball position at every voxel. A physical state in quantum field theory is a linear combination of configurations. And that is quantum field theory. So there's nothing magical here. We just had one system, and we realized that same system is reproduced throughout all of space. We quantize that one system, and then we quantize the constellation of all of those systems using the idea of tensor product. And that is quantum field theory. So remember I mentioned in quantum field theory, we got to do a couple of things. In any quantum mechanics problems, we first have to define our Hilbert space and our relevant operators, and we've done that very explicitly now. We now have the Hilbert space where all the action will take place in quantum field theory. It's the most important thing, and we have our relevant operators. We've talked about three of them. The phi operators, which are taken from each individual voxel, but could be applied to the whole Hilbert space. The localized momentum operators called pi, which are taken from each individual voxel, but again, it can be applied to the entire Hilbert space. And these operators, the partial derivative operators, d phi dx for x is 1, 2, or 3, and these are each one's taken at different points in space of different voxels. Now, just like in ordinary quantum mechanics, what are we going to do next? Our next goal will be to define the Hamiltonian operator h for our system. That becomes very important for reasons I mentioned initially. How do we do that? Well, in regular quantum mechanics, a lot of times we'll just ad hoc throw something in there or just grab some idea semi from classical mechanics or experiment. But here we're really trying to find the fundamental laws of nature, and luckily we have some very deep aesthetic, physically satisfying ways of doing it. And we'll appeal to principles, to deeper principles, and also something called classical field theory, which we'll go over in the next lecture. That's it. Thank you.